Hi everyone, we're glad to welcome you once more to Best Science Brain YouTube channel. Today, we're going to look at determination of the endpoint of WAEC March June Chemistry Alternative B Chemistry. So, in this titration, you'll be given the acid and the alkali or base. The acid is labeled D, not A as usual. So D for the acid, and the acid is triazole 5 acid. Then you're also given and that you have 5 CN cube, 1 DN cube. That is 5 CN cube acid in 1 DN cube solution for D, which is HNO3. While our E, the base, is sodium carbonate, we have 3.5 grams of the carbonate dissolved in also 1 DN cube of solution. So we have the format for reporting our titration on the board. WAEC 2024 20B. Pipette, volume pipette we use 25.00 CN cube as usual. Indicator is methyl orange. Color change is yellow to orange. We have our buret readings in CN cube. Unit is compulsory. Very important. Final readings. Initial readings. The volume of D used. The D is the acid now. The rough, the first, the second. You can also do the third one if you wish, but if you do 1 and 2 and are consistent, there's no need to do the third one. So let's go to the question right now and start the experiment. Question says solution D contains 1.28 gram triazole 5 HNO3 acid in 250 CN cube. Solution E is S2CO3 bicarbonate containing 1.75 gram of the substance into 500 CN cube of water. Put D into the buret and titrate with 20 or 35 CN cube portions of E using methyl orange indicator. Repeat the experiment to obtain consistent readings and tabulate readings. And they will have calculations. A, calculate the average volume of acid, that is of D used. Then B, we have other calculations which we're going to do after the experiment. So let's go to the experiment now. So this is our D, the acid. We're going to empty it into the buret. So when you add, you check whether it's leaking. It can come down. It's not leaking. So since it's not leaking, you continue adding. That's a precaution. So we're adding the acid, which is D, into the buret. I'll add until it's above 0. When it's above 0, I return the acid container, as you can see, under the buret. And then when I do that, I remove the funnel to avoid additional drops of the acid, and then adjust the acid until I start from 0. So I can adjust it by opening the top, drop by drop. So yeah, it is at 0 now. So it's at 0 now. So you can see that intact. So that's 0 now. So we'll now report our work. Here we'll now write initial volume under rough as 0.00. 0.00. The next we'll do is we pipette the base, and the base is your solution E. So this is your base. So you're going to prepare the base, take it up, and then prepare the base. Then you adjust the handle little. Allow it to be going down. Oh, it's down. Until the bottom of the cork sits on the meniscus. The bottom of the meniscus, that is the cork, sits on the ring. That one you have exactly 25 CN cube. So I like to go gradually. If it's going very fast, you miss the mark. So one with the bottom of the cord sits on the ring, you cover it. So we have it there. So we'll now take it to this place, into the neat conical flowers. So after that, we bring our indicator, methyl orange, freshly prepared. So you take using the drop-in pipette. Let me adjust it. Okay. It's still much. Adjust the tip and the tone. So you take some indicator, bring your base, add 1 drop, and that drop. Don't add more than 2 drops. You can use 2 drops, you can use 3 drops, but be consistent. If you're using 2 drops, use 2 drops all through the experiment. If you're using 3 drops, use 3 drops all through the experiment. The color is faint, so I'm going to use 3 drops to make it more intense. So that is it. So I can see the yellow color after adding 3 drops. So we'll now start our experiment. We'll go to the titration. You see it's still intact. And we'll level it to 0. Remove the acid container and keep it away. Bring a white tile. But we're going to use a filter paper as an improvised white tile for accurate color change. Keep it under, and then bring the conical flowers. Open the tap. Allow it to go slowly. So it's going slowly, as you can see. That's the first one we're doing. So you have to take it slowly. Slowly as you watch the color. Any color change reflect on the white paper. So your focus should be on the white paper. So you're going drop by drop, and then you have to be ready for action so that when you notice a color change, you close the tab. So that's the way it's being done. The color is changing gradually. So we'll close the tab. So let's shake it and see what has happened. So we have an orange color produced. You look at it, the difference is clear. Different from yellow. It's glittering in appearance. Have an orange color produced. And the volume of acid in the buret here is 20.70. The final volume 20.70. So we'll go to the board and report. Final volume of acid as 20.70. We'll subtract. We'll have 20.70 here. So before we go to the first experiment, you can use your rough, not on your exam paper, your rough, and make an estimate. The estimate is this. Let's assume that this is correct. And this is 20.70. This is the correct value since we took our time to do it. And then let's assume you want to start from one whole number. No longer 0. You must not start from 0. You want to start from one whole number. You add 1 to 20 to give the final. I'm going to give you 21.70. If you add this, you have this. So what do? You're going to pour more acid into the buret to start from one, and adjust one whole number as the initial. Then you run the acid speedily. You run the titration speedily because you know where the endpoint lies by virtue of doing this one carefully. So you run the acid speedily to 21.70. But you not reach 21.70 because it must definitely change before 21.70. So you run it to the whole number before this value. The whole number before this is 21. Run it to 21. So when you reach 21, you now take it drop by drop. You must surely change between 21 and 21.5. So let's remove this. So our initial is 1.0. Then we'll now run the titration. We're going to add more acid. and adjust to 1.0 and then run the titration to see when we're going to get exactly this tighter value or something less. Remember, we're running it to 21 and then after we reach 21, we'll take it drop by drop. Now when I'm adding more acid, that is solution D, into the buret. So take it up to above 0. Bring back the acid container to the base of the retor stand. Then we now open the tap to adjust the acid level to 1.0. So you see it's coming down. So gradually we can see increase it as much to 1.0. So we are there at 1.0. Okay. So we have a conical flask, the one we use for the experiment. The mixture have been poured away and it rains only with distilled water. Rains only with water, distilled water. Then we're going to pipette, repeat the size, pipette the alkali again, the base again. Then allow little air to be entering and watch the mark. So when the bottom of the meniscus sits on that ring, you have exactly 25 cm cube. It's almost there. So it's there. So we bring our conical flask, put it inside and allow it to run through into the conical flask. So after that, you just drop it and remove it. Don't blow the last drop. It's a precaution. Then you have your methyl range, freshly prepared. We'll collect with the pipette, dropping pipette. Deliver 2 drops and then the 3rd drop. Since we started with thread, so I will continue to use thread all through. Be consistent. Thread with thread, so I'll have to continue to use thread. So I have to shake it. It have a yellow color, bright yellow color. Then we bring it under the buret and start. So we started the titration from 1.0 on the top. I make it to run faster now. So it's going faster because I have an idea of the end point. So I have an idea that it's going to change around 21. So it's going faster. So when it reaches 21, I will close the tap from my estimate. So we've got to 1.7 and the whole number before the 1.7 is 21. So reach 21, I'll close the tap and take it drop by drop. One drop is about 0.1 cm cube. So we're moving. It's around 13 now. So this time around, since you have a gauge, your focus will be on the buret. So when you reach 21, you close the tap and take it drop by drop, and then your focus will not be on the conical flask because it's approaching the color change. And between 21 and 21.5, it will change. So we're moving around 18 now. It's going around 18.5 now. Then around 19.5, going to 20. Then we have 20. We're coming close to 21. So this 21, I'll pause the buret. So I've done that. And I like to go drop by drop later. So you're going drop by drop. Drop by drop. You can see the way it's going. Drop by drop. This time around, my focus is in the color change. I'm looking at the paper for any color reflection that will take place instantly. So I've observed a little color change. So let me close the tap now. So close the tap, bring out the conic and shake it. So you have a yellow glittering orange color. Glittering orange color. And the buret reading at this point is 21.30. 21.30, the final reading on the buret. So report on our table or report on the board 21.30. If you subtract, we have 20.30 as our theta value for number one. You see, this one is somehow lower than this. That means the rough, we tried in the rough, but we overshot by more than 4 extra drops to 5.7, but this is more accurate. So if this is accurate now, if you call here 21.30 and you wish to start from, let me say, you wish to start from 10.00, you can choose any component value. That means the final now going to be add, you have 30.30. That'll be the final. So I'm going to start from 10 and then expect the color to change around 30.30. The nearest whole number to this is 30. So I run that seed until I reach 30 with the nearest whole number to this value. When I reach 30 with speed, when I reach 30, I'll now take drop by drop between 30 and 30.5. It must definitely change. So I clean off 30.3 and this, because this one's estimated. But you don't write these things on your paper. This could be on your rough. Don't alter your table. So then we're going to now do the experiment starting from making the initial to be 10. So let's add more acid to the buret. So I'm going to top the acid, that is solution D, into the buret again. Remember that we want to start from 10. So it's above 10. I'll remove the funnel as a precaution to avoid additional drop of acid into the buret. Then I'll open the tap and adjust the level of the acid to 10. It is 10 when the bottom of the minute screw sits on the 10 cm mark. So let me move it faster. It's going inside, as you can see under. So we're moving to 10. Once it's 10, I'll close the tap. So we have 10 as initial, the tap closed, and that is what we recorded here. Then we'll move to the base. So we can see that we are already collected, pipetted 25 cm of the alkali into this place. Remember that after each experiment, you have to wash the conical flask with water before you pipette under alkali. We now collect our methyl orange using the drop-in pipette. Then, as we observe, using 3 drops, 1, 2, 3, added into this place. So we shake it. So as you can see, you have the yellow color of the methyl orange in the alkali. So we're going to start the experiment now. So we'll start the experiment now. Open the tap. Remember the initial is 10. So open the tap and allow the acid to be running into the alkali. As we remember, we said we are moving to 30. Then we can increase the rate or the tap rate. It's going faster. So once it reaches 30, we'll close the tap and take it slowly. So you can see that. You are still on to Best Science Brain YouTube channel. If you are seeing this video for the very first time and you are not subscribed yet, please move up to the channel's name Best Science Brain. And the video is playing. Under the video, you have the channel's name Best Science Brain. You have the subscription button or icon, the subscription bell, tiny bell below the channel's name Best Science Brain. Tap on it once and get subscribed if you're not subscribed to the channel to be seeing our video, our tutorial classes on chemistry and physics and mathematics from time to time. If you wish to contact us personally, you can send us an email to Best Science Brain Gmail, or you can go to Facebook, search out on Facebook Best Science Brain, the same name, and send out an inbox message. We'll respond accordingly. So moving close to 30 now. So we are almost there. At 30, I'll turn off the tap. So I have done that. So having done that, then I'll open the tap again for it to go slowly, drop by drop. So it's going drop by drop. You can see that happening there, drop by drop, one drop at a time. You can see that it's moving drop by drop and approaching the color. We're now watching this place for a color change. So I think we're almost there. It's having some orange color. So having done that, I will close the tap, bring out the conical flowers and shake it. So you see, we have the glittering orange color. If you compare the colors you obtained today, they're all the same. And the final reading we have on the buret there, after looking at this, is 30.30. 30.30. So report our work here. We have 30.30. When we subtract, we have 20.30. So you see that these two readings are consistent, they're very accurate. So I don't need to do the third one. That would be a waste of time in the exam hall. Whether you do 2 or you do 3 times after the rough, you get the same mark. Because it's marked this way. Each column, they mark 2 columns. Each column gives you 4 marks, 4 marks, 8 marks. Even if you do it 3 times, they only mark 2. Then we'll now find our average VA, that's the endpoint. 20.30 plus 20.30 all over 2, since we're using 2 values. I don't have to use the rough. The rough is wide or far from this. If you divide and add and divide by 2, you have VA as 20.30 cm cube. That's the end point for this experiment, 20.30 cm cube. So if your endpoint in your own school agrees with our own endpoint, use our endpoint. That's okay. Agrees by what? By plus or minus 0.10. That is the range. If you subtract 0.1, that have 20.20, 20.30. If you add, have 20.4. Subtract 0.1, 20.2, add 0.1, 20.4. The mid value, 20.3. So your endpoint, your school is 20.2, 20.3, 20.4. You can use our own endpoint. But if your endpoint lies, the value is away from this range, you have 21, 20.5, or your teacher gave you 22.2, use your teacher's endpoint if it differs from this endpoint. So we're going to go to calculations for this experiment. We're going to go to calculations for this experiment, and then we're going to choose 2 different calculations, all of them centered on this particular endpoint. So go to calculations, do the first one, so do the second one. So we'll now see how it works out. Question B says, from your result and information provided, calculate the concentration of D in mole per dm cube. Remember that D is the acid, the conc of D in mole per dm cube. So let's look at the question again. We're told that solution D contains 1.28 gram of HNO3 in 250 cm cube. Solution D contains 1.28 gram of HNO3 in 250. So let's go to calculation on the board. Now I have from information the paper says 250 cm cube of solution contains 1.28 gram of D, that's HNO3 acid. So you find the mass that should be in 1000, and that's what we call the mass concentration in chemistry. 1000 cm cube now contains 1000 times 1.28 all over 250. So when we do that, we're going to have 5.12 gram per dm cube. So this is the concentration or mass concentration of solution D. Concentration of a D or acid. So find the molar mass of the acid. The molar mass or the molecular mass of the acid, they call it molar mass of the acid, HNO3, is the mass value given to you in bracket as 1, nitrogen is 14, oxygen is 60. All the values are given to you in the bracket. Multiply by 3. When you solve, you're going to have 63.0 gram per mole. Keep your calculations to 3SF. Look at it. 1, 2, 3. 1, 2, 3. 3 signal figures, not decimal places. So we're looking for the concentration of D, the conc of D in mole per dm given by the conc in gram per dm, which is the mass concentration all over the molar mass. So that becomes 5.12 over 63. Making substitution, we now have the answer as 0.0813 mole per dn³. This value is given also to 3SF. So whenever you say equal to, what comes should be in 3 centigram figures, please. If not, you lose your mark. So take a minute to look at our work as we go to the next question. Question II says concentration of E in mole per dn³. Mind you, E is the S2CO3. That is S2, that is the unknown carbonate. So we're looking for the conc of E in mole per dn³. So let's go to the board. So to find the concentration of E in mole per dn³, E is the carbonate which acts as the base. So, and D is the acid. So from my question 1, our CD we obtained before this question is 0.0813. That is the concentration of acid in mole per dn³. Then our VD, that the average titer or the endpoint, is 20.30 from my experiment. Our VE, the pipette, that the base, is 25.00 cn³. Then the mole ratio of ND to NE. ND is the acid, NE is the base. Ratio is the number of moles in front, 2:1. So 2:1. So you have everything provided for you except CE. You apply the titration formula CdVd all over CeVe equal to ND over NE. Look like the one you use CaVa over CbVb. The only difference is replace the A with D and then replace the B with E. They make CE the subject. CE becomes equal to CdVd times NE all over VE times ND. You make your substitution. The value of our CD is 0.0813. Our VD is 20.3, the endpoint of your table. Your NE is the mole ratio of the base is 1. Our VE, the value of the pipette, is 25. Our ND is 2. So when we solve all this, we're going to get 0.033 as our answer. Remember I told you run it to 3SF by putting another 0 at the back, which is 1, 2, 3 mole per dn³. So this is the base concentration according to question number 2. So take 1 second to look at a solution as we go to question number 3. So question 3 says we have to find the relative molecular mass of H2CO3. Remember that the compound is unknown to us now. So let's go to the paragraph and see what is any clue. They say solution E is S2CO3 containing 1.75 gram of the substance in Faraday cn³. They give us the mass of the substance dissolved in Faraday cn³. So all we're going to do now is to find the mass that should be in 1000. That will become the mass concentration of H2CO3. So let's go to the board. So for the instruction we have on the paper, Faraday cn³ solution of E contains 1.75 gram of H2CO3. So we'll find the mass in 1000. That becomes the mass concentration or the concentration in gram per dn³. Will now contain 1000 cn³ times 1.75 gram over 500. So when we solve this, cn³ cancel, say we're going to get 3.50 gram per dn³. So to 3SF. And remember, this is our PB, that is concentration in gram per dn³, not PED this time around, but PE because that's the basis E. And remember, we got our CE from question number 2. The previous question we got our CE as 0.03330 mole per dn³. And you know in chemistry that relative molecular mass or molar mass again by concentration in gram per dn³, which is our rho E here, all over the concentration in mole per dn, which is our CE. We'll now substitute 3.50 by all over 0.033. So when we solve this, we're going to get 106 gram per mole. This is the molar mass. But since we are asked to find the relative molecular mass has no unit. So leave the answer as 106 without any unit on it. So that's the answer to this question. Take a minute to go through this work. So as we go to the next question. So question IV says find the RAM of S. RAM means relative atomic mass of S. So let's go to the board. So since on question BII, the relative molecular mass of this compound S2CO3 is 106. So what do? We now equate this compound S2CO3 to 106 and then look for the value of S. We now say 2 times S because of the 2 atoms of S there plus the mass of carbon is 12, all this is 16, all these values are in bracket, multiply by 3, we got 106. So we have 2S plus 3 times 6 is 48 plus 2, that is 60, what 106. Taking like terms together, 106 minus 60, that gives us 46. So S becomes 46 over 2, that gives us 23. We put 0.0 to make it to 3SF. And the relative atomic mass has no unit, just like relative molecular mass. So don't put any unit on it. So go through the work, go to the next question. Question V says percentage by mass of S in S2CO3. Percentage by mass of S in S2CO3. So let's go to the board. So we know that from our previous questions, BII, the molecular mass of S2CO3 it was obtained as 106. And from BIV, the relative atomic mass of S, we obtain it as 23. We're looking for the mass of S inside this compound. So there are 2 atoms of S in this compound. So mass of S in the compound becomes 2 times 23. 623 is the mass of 1 atom. That gives us 46.0 grams. Please put 0.0 to 3SF. So percentage of S in the compound becomes mass of S all over relative molecular mass of S2CO3, that the compound times 100 over 1. Making a substitution, the mass of S is 46, the molecular mass of the compound is 106, then times 100. And that gives us 43.4% to 3SS. So check our answers. Whenever I put equal to, what accompanies the equal to is 3SF. So go through the work in a minute, in a jiffy. So go to the next question. Number VI says volume of CO2 liberated at STP during the reaction. Volume of CO2 liberated at STP during the reaction. So going to the equation, we have to first of all write the balance equation for the reaction. This is the CO2 we are looking for. A question mark on it. We'll connect it to one of the reactants. We can choose the carbonate. So we have 1 mole of the carbonate, 1 mole of S2CO3 liberated, 1 mole of CO2. Then, having done that, we can now also say 1 mole of S2CO3 liberated, 1 mole of a gas at STP is 22.4 dN cube of CO2. So therefore, since in the reaction, the number of moles of this carbonate is the molar concentration, and that is 0.033 mole of carbonate. We now liberate 0.033 times 22.4 dN cube, and that gives us 0.739 dN cube of CO2 liberated at STP. You can keep your answer in dN cube, or you can keep your answer in centimeter cube, which is going to be 739. You multiply by 1000 to convert to cm cube. So this or that is okay. So look at it. So if a student decides to connect with acid 2 moles of acid to 1 mole of the student is also correct. So use 2 moles of the acid to 1 mole of the CO2, 2 moles of the HNO3 to 2.4. Then now use the acid molar concentration is 0.0813 and then solve. You're still correct. So take a minute to look at the work and to go on. So we are coming to the end of the calculation on the titration experiment that we did. So you know that question can be framed in different ways in the examination like this. So you don't expect the question to come verbatim the way the specimen is provided. So there are different ways or different angles from which the question can be set. Now we're going to take another question, another set of questions from using the same specimen, using the same endpoint we got as 20.3 to solve it. The same specimen, and then you're going to see the correlation between the first question and the second one. But in this one, what we're going to look at is going to be on question that involve water of crystallization. You know that sodium carbonate is a compound on a hydrous form. Well, we use the hydrous form quite alright according to the specimen for the experiment. But they can give you a question and frame it and make it to become hydrated, and you're asked to look for the water of crystallization and other things. So let's look at such question and see how we're going to solve it. So let's look at this question that says solution D is 0.0815 mole per dn cube HNO3 acid. So solution E was prepared by dissolving 4.72 gram of hydrated sodium carbonate in 500 cm cube of water. Put D into the buret and titrate with 20 or 25 cm cube portions of E using methyl orange indicator. Repeat the experiment to obtain consistent readings and tabulate your readings. So we have done the experiment so far, so we're not going to repeat the experiment, and we've got the same endpoint 20.3. We're going to use a calculation. Then A says calculate the average of D used. We have done that 20.3, the endpoint. B says from your result and information provided, calculate the const of E in mole per dnq, the conc of E in mole per dnq. The E is the base. Now, to find the conc of E in mole per dnq, don't look at the question again and see whether they gave us the conc of D. If you go up the first sentence, we're given the conc of D directly here. The const of D is 0.0815 mole per dn cube. So let's go to the board. So we'll start with the first question. We're looking for the concentration of E in mole per dn cube. We don't know that. We're asked to find. And from the question, we're given the question of D. D is the acid, which is 0.0815 given to us in the question. 815 mole per dn cube. Then we need the volume of the acid, that's the average titer, 20.30, which we obtained in the experiment. Then our VE is the pipette, which is constant as 25.00 cm cube. Then we need the mole ratio, which is the ratio of the acid to the base. Acid is the D and the base is E. You get it from the balance equation. There are 2 moles of the acid here, and the coefficient here is 1. In front of this is 1, so it's 2:1. So having obtained everything except one item, you apply the general titration formula CEVE all over CDVD equal to NE all over, okay, let me put it this way, still right, but let's put the acid on top and put the base under, then all over ND over NE. So make CE the subject. So CE becomes CDVDNE all over VE times ND. Make a substitution. Our CE becomes, the value of your CD is substitution 0.0815. Our VD, the average titer 20.30. Our NE, the mole ratio of the alkali is 1. Then our VE, the mole ratio, that is the volume of the pipette, 25. Then our VND, the number of moles of acid, that is 2. So when we solve this, our answer is going to be 0.0331 mole per dn cube. So you can compare the answer in the two questions that are similar. So take a minute to go through this work as we go to the next question. We now go to BII that says the concentration of anhydrous sodium carbonate in gram per dm cube. The concentration of anhydrous Na2CO3 in gram per dm cube. So let's go to the board. So we're looking for the concentration of anhydrous, that the compound, the salt without any water attached to it. That one says anhydrous in gram per dm cube. And we'll call it PE or rho E, since AE stands for the base. I remember that from the previous question from BI, we got our CE as 0.0331 mole per dm cube. So we'll calculate the molar mass of the anhydrous compound of Na2CO3. So in this case, they gave us the full compound. The sodium is, in bracket is 23, the mass of sodium. Carbon is 12, also is 16 multiplied by 3. And that gives us 106 gram per mole if it's molar mass. But if you write relative molecular mass here, if you have put R here, remove the unit. So it's a difference. But if you call it molar mass, you put a unit on it, gram per mole. So let's return to why anyhow one is okay. If you call it molar mass, gram per mole is here. They're looking for the concentration in gram per dm cube. You know that the concentration in gram per dm cube, which is called the mass concentration, that is rho E, is given by the molar concentration CE times the molar mass. So making a substitution, our molar concentration is 0.0331. Our molar mass is 106 for the hydrous compound, and that gives us 3.51 gram per dm cube. So that is it. So take a minute to go through the work. We'll go to the next question. Go to question triple I that says mass of water in the hydrated compound, sodium carbonate dot S water. That will give the mass of water of crystallization in this compound. To solve this, we have to go to the question and look for a clue. We're told that solution E was prepared by dissolving 4.72 gram of the hydrated carbonate in 500 cm cube. So what we're going to do now is we're going to find the mass concentration of the hydrated, not hydrated carbonate, because the hydrated compound that contains water. So this is the formula of the hydrated compound, contains water. So we're going to find the mass concentration of this compound using this information. We have here that 4.72 grams of the hydrated compound is dissolved in 500 cm cube of water. So we find the mass that is going to be in 1,000 before we do the calculation. So from the question, we have this information given to us that 500 cm cube solution contains 4.72 gram of the hydrated compound. So we're going to find the mass that should be in 1,000 cm cube. 1,000 represents the mass, that is 1 d cube. The mass in this represents the mass concentration. That becomes 1,000 times 4.72 over 500. So when we solve this, we'll be getting 9.44 gram per dm cube. So this is the mass concentration of the hydrated salt. So we're looking for the mass of water. So mass of water or mass concentration of water, I will call it, will become mass concentration of the hydrated salt, that is N2CO3S water, minus mass concentration of the anhydrous, that one we got in question BII. So that is the difference between these to give the mass of water. So substituting, the mass conc of the hydrated is this one, 9.44, and the mass conc of the anhydrous we got in question BII is 3.51. So we'll subtract these values. We have so let's have 5.93 gram per dm cube. So this is the mass of water in the salt. So take a minute, go through the work as we move on. So the question IV says the percentage of water in this compound, that is the percentage of water of crystallization in this compound. So let's go to the board. So to find the percentage of water in the compound, we need the mass concentration of water, which you got in question triple I as 5.93 gram per dn cube. We also need the mass concentration of the hydrogen salt, that is N2CO3 dot SH2O, which we got as 9.44 gram per dn cube. So the percentage of water will now become the mass concentration of water in the salt all over the mass concentration of the hydrated compound multiplied by 100 over 1. So have it there. So that's going to be 5.93 by substitution all over 9.44 multiplied by 100. So let's press our calculator and have the correct answer. So we now have 62.8% to 3SF. So that is the water inside the compound. So you go to the work as we go to the next question. Question V says we should find the value of S. The value of S. S represents the number of water molecules of crystallization in the compound. So before we go ahead to find the value of S, which is the number of water molecules of crystallization, we have to first of all find the relative molecular mass of the hydrogen salt. So we have to first of all find its molecular mass or molar mass. Then the concentration of the hydrogen salt in mole per dn cube. You should know that the concentration of Na2CO3 in mole per dn cube, the hydros, which is our Ce. So the concentration of the hydrous salt, sodium carbonate in mole per dn cube, that is Ce, is the same as the concentration of the hydrated salt in mole per dn cube. They only differ in their mass concentration because of the amount of water added to this one. So the concentration of this substance in mole per dn cube and this one, the hydrated counterpart, are the same. And our Ce, we got our Ce today as 0.0331 mole per dn cube. We also obtained the mass concentration of the hydrated salt, or that is this compound. We got it today in question, I think BVIV, as 9.44 gram per dn cube. And we're looking for the molecular mass or the molar mass of this compound. And you know that molecular mass or molar mass given by concentration in gram per dn cube all over molar concentration. The concentration of the substance or the hydrogen salt in gram is 9.44 from the previous calculation, while the value of our Ce, that the molar concentration, is 0.0331. So when we divide this, we get in 285 as a relative molecular mass to 3SF of the compound. We want to put it in form of molar mass, you now say gram per mole on it. But if you say molecular mass, no unit. So having done that, we're looking for the value of S. That means the weight of this compound is 285 grams. We now say Na2CO3 dot S water equal to 285. We now calculate S. To evaluate S, we place all these elements with their atomic masses. From the bracket, solid 23 multiplied by 2, carbon is 12, 1 atom, oxygen is 16 multiplied by 3 because of 3 atoms. And then replace the dot with plus, remove it and put plus. Then S, the molar mass of water is 18, equal to 285. If I add up everything here, I have 106 plus 18S, giving us 285. So take a minute to go through the work before we wipe the upper side and continue from there. Now continue from where we stopped. Collect items. 18L becomes 285 minus 1. 285 minus 106. So 285 minus 106 will give us 179. So make L the subject. S now becomes 179 over 18. That gives us 9.94. But since the value of S is always a whole number, so it's the number of water molecules. So the next whole number will give us 10.023 SF. So that is it. So we have come to the end of this exercise, which is focused on determination of the endpoint for alternative B, Practical Chemistry 2024 WAEC examination. And then we have done some exercises to show how WAEC can showcase or how they can frame questions. Don't be surprised if you enter the exam hall and you have the chemicals in a different dimension, a different form. Because they can twist questions, but the calculation remain the same pattern. So copy down the calculations, don't memorize them, but know how they are done. Learn and study very well. Also, when you are done with this, refer to our channel, streamer channel, and look for where we did the NACO 2024 Alternative Practical Chemistry. That is chemistry, NACO chemistry. The calculation, the specimens are similar. The specimens they brought in this WAEC and the specimen they were brought in NACO are similar specimen. So also look at the calculation we did for NACO and then observe the similarity. That one calculation we did there that is somehow that had to do with solubility of the sodium carbonate, which we couldn't do in this video. So go to that one and study how to calculate solubility of salt. So it's done in that of NACO specimen. So NACO chemistry specimen, which is in the channel already. So very soon we're going to provide the qualitative analysis, that the test for the anion and cation, that is specimen F, which we're going to do for this alternative B practical chemistry. Remain connected. Refer your friends to this video. Share this video to your friends, to your group of friends, to your classmates on WhatsApp group. Let them understand how this is being done and pass the exam as you wish to pass. So don't be selfish. Share the video. Then you are not subscribed to the channel and the video is playing. Go to the channel's name, Best Science Brain. Under the video, you have Best Science Brain, BEST, Best Science Brain. And then under it, you have the subscription button. Tap on the button only once and get subscribed. So whenever you see a video, our video is always unique and attractive. We'll explain to the core. So subscribe, remain connected, like our video, share, connect other people. We thank our subscribers all over the globe. Thank you very much for all that you're doing. For without you, cannot be here. So thank you very much.